Hello guys, how are you today? So today I'll be explaining AP Chemistry Chapter 3 summary. So I'm gonna do a quick summary for Chapter 3. We'll start with the very first section, which is section 3.1. The section starts with explaining to us why do atoms bond. First of all, take any regular atom. For example, let us take potassium, Na. Let's write its configuration. 1s2, 2s2, 2p6, 3s1. This is the configuration of Na. Now, take the nearest noble gas to Na, for example, neon. It would be 1s2, 2s2, and 2p6. Now, what do you notice? Hello, is not letting me write P. Yeah, there we go. What do you notice is the difference between sodium and neon, other than like they have different configuration? We notice that in neon they complete a full valence shell, meaning they complete a full energy level N. Now, if you look at sodium, on the other hand, it does not complete a full valence shell, because if you look at the very last S, which is in the scenario 3s1, you will see that it did not complete the full N3 orbital. It did not. Or in better terms, it did not complete the full N3 shell. So due to this, we say that noble gases have what they have a full valence shell, right? Now, of course, the other elements that are not noble gases will definitely prefer, to obtain a full valence shell. So this gives us our first part of the sentence, which is that atoms tend to obtain a full valence shell. Now, why do they tend to obtain a full valence shell? Well, we know that elements, as a very single atom, of course, if they're not noble gases, are very unstable. They tend to react very quickly. So, because they are unstable, they tend to react more quickly. They may be considered dangerous. So what do we say in this scenario? We say that they tend to obtain a full valence shell to become more stable. So before bonding, they are unstable. After bonding, they become what? They become stable. And as well, to decreasing their energy, because we said that they will be very reactive. So if they're very reactive, that means they have a lot of energy. So they become more stable and they decrease their energy by what? By reacting with other atoms and forming a chemical bond between them. Okay, so this is basically the introduction on what is a bond. Okay, we know that a bond results because that atoms want to be more stable, obtain a full valence shell, and decrease their energy. So they react with other atoms to form a bond in between them. Of course, we have different types of bonds. In this chapter, we're only going to be discussing 4 different types of bonds, which are ionic, metallic, covalent, and coordinate or dative bonding. And just like that, in the very first chapter, or very first section, 3.1, we go to the first type of bonding we have, which is ionic bonding. Okay, from the name ionic bonding, we derive the main thing that acts, which is an ion. Ions, what are they? They are electrically charged species. What does this mean? This means they have either a positive charge or a negative charge. And their positive charge or negative charge allows them to attract and repel. If they're the same sign, they will repel. Opposite sign, they will attract. I meant to say attract, okay? So, how do ions form? They are formed when atoms gain or lose one or more electrons. E- means electron. So Ions are electrically charged species, either positive or negative, that are formed when atoms gain or lose electrons. Now, why isn't it protons? Well, very simply, if you remember, from the structure of an atom, we have the nucleus that has the neutral particles, then the positive particles, and then what do we have surrounding that? We have surrounding that the electron shells that contain what? That contain the number of electrons. So we don't ever touch the nucleus, instead we touch the electrons. Now, what are the different type of ions? We have cations, which are positively charged ions, which occur when there is a loss of electrons. And then anions, which are negatively charged ions, and they only occur when there is a gain of electrons. Now, speaking on the periodic table, okay, about metals and non-metals, we say that metals are usually cations. So metals usually lose electrons. Okay, that's why they are cations. And then non-metals usually gain electrons. So that's why they are what they are, anions. Now, inferring from this, we can start discussing ionic bonding. What is ionic bonding? Ionic bonding is when a metal and non-metal, what do? They exchange electrons. So, ionic bonding occurs between metal and non-metal. Okay, for metal, I'm gonna say M. For non-metal, I will say NM. Okay? So, what happens for ionic bonding to occur? The metal gives electron to non-metal, right? So, when the metal gives electron to a non-metal, the metal loses electrons and the non-metal gains electrons, right? So what happens when we have loss of electron and gain of electrons? We will then have a cation and an anion. So when a cation and an anion react together, they will form what? They will form an ionic compound, right? And as a result, what we can say? We can say that it will have noble gas configuration. So they bond in order to have a full valence shell, or in other terms, noble gas configuration. So let's take an example of an ionic compound. For example, we can take NaCl, which is Na plus, and Cl minus. So let us draw exactly what's happening. Na, if we draw the whole atom, it will look like this. Na, surrounded like this, right? And then it has this as well. Okay, and then it has the third and final shell in which it has the last electron. So this is the configuration of Na. This is the cell of Na. Now for Cl, it would look like this, the atom. Right, and then last but not least, we have 1, 2, 3, 4, 5, 6, and 7. So as you can see, we said it becomes Na plus and Cl minus. What does this mean? This means Na loses an electron, whereas Cl will gain an electron. So now, if we drew how they looked like, it would look like this. The representation, of course, it would be in brackets Na with the outer shell that doesn't have anything with it, plus, and then Cl with the outer shell that has 1, 2, actually let me change the color. Let me change this to red and blue again, okay? So this would be what? This would be red, so it would be Na outer shell without anything because we gave the electron plus, and then the blue one would be Cl. It would be Cl with the outer shell having 1, 2, 3, 4, 5, 6, and 7, and 8 electrons. So because it gained an electron, it will be what? It will be Cl minus. So this process is called what? This process is called ionic bonding, and it results in something called what? Called an ionic crystal lattice if there is multiple of these ionic bonding together. So ionic bonding will result in an ionic crystal lattice. Now, another term that we can use instead of ionic is electrovalent. So we can say that an ionic bond is the same as what? Is the same as an electrovalent bond. All right, now we discussed just like a few seconds ago that a bunch of ions together is called an ionic crystal lattice. To be more specific, an ionic crystal lattice is a regular pattern which is repeating, so a regular repeating pattern which is repeating of ions. So it's a regular repeating pattern of ions. Now I'm gonna add an image over here and I will explain what is coordination number. So what I have placed in front of me is an ionic crystal lattice. What about this ionic crystal lattice? As you can see, it's a regular pattern which is repeating of ions. So a regular repeating pattern of ions. Now, I mentioned something earlier which is coordination number. Coordination number is what? It's the number of ions surrounding an ion in a crystal lattice. So number of ions surrounding an ion. For example, let us take this Na plus over here. How many ions are surrounding it? We have one here, one here, one here, one here, one here, and one here. So in total it has 6. So this Na plus ion has 6 surrounding Cl minus ion. So what can we say about this? We can say that the coordination number of Na plus is how much? Is 6, okay? So this is very simply the definition of a coordination number. Now, there is a concept which is on why ionic bonding is very strong. Very simply, we can say that ionic bonding is very strong due to multiple electrostatic, it doesn't fit, I'm gonna just erase it and write it again, electrostatic forces of attraction. Okay, so ionic bonding is very strong due to multiple electrostatic forces of attraction. And now, with this being said, we can say the higher the magnitude of charge, I think I clicked the eraser by accident, the higher the magnitude of charge, the greater the attraction. Now, after we finish this, we will need to discuss how to draw ions. How do we represent ions? We represent them using something called the dot and cross diagram. So what about this dot and cross? I'm gonna say this orally. Dot and cross diagrams use dots to represent only the valence electrons of one atom and crosses for another atom. They are just a representation. This does not mean that the atom actually, the electron actually looks like this. No, it's just a representation. Now, let us say the rule for an ion x to the power of n plus and y to the power of m minus. Right? So an example of this would be Na plus, or it could be N3 minus, for example. Okay, let us represent both of these. We first of all start with what? We start with representing Na plus. We first start with brackets, okay? All of the ions are enclosed in a square bracket. Perfect. Now, let's say we're dealing with Na plus. We put Na. We see, is it positive or negative. In any scenario that it's positive, you just draw a circle and you leave it empty. This is the valence outer shell. It's empty. After this, what do? We put on the top right corner the charge. So in this scenario, it's plus. Now, let us deal with N3 minus. Again, we said it's enclosed in square brackets. And then we draw N and we draw the valence shell. How many electrons does nitrogen have in its valence shell? It's supposed to have 5 electrons. So 1, 2, 3. Actually, no, we don't draw it like that. Don't follow how I was drawing it before. We do 1, 2, 3, 4, and 5. Okay, so this is what? These are the 5 nitrogen electrons. And then what do? We do that it gained electrons. How many electrons does it gain? It gains 3 electrons. So 1, 2, and 3. Of course, they must be represented in any different form. They can be a different color. They can be a different shape. For example, dot and cross, right? So as long as it's different from the electrons of nitrogen. And then what do we put on top? We put the charge on top. So it's gonna be N3 minus. Okay, so as we come to a conclusion about the ionic, I'm just gonna infer what is the octet rule and the duplet rule. The octet rule is when the valence shell has 8 electrons, and the duplet rule, oops, did it erase that? Oh no, it erased that, my bad. There we go. Okay, I think it just wants to piss me off today. Wait, what's it doing? Okay, so octet rule means that the valence shell has 8 electrons. I can't even do anything, what the hell, wait. Okay, there we go, I fixed it. So the octet means that the valence shell has 8 electrons, whereas the duplet means that the valence shell has only 2 electrons. Example of the octet shell would be, for example, chlorine Cl minus. It would be what? It would have 1, 2, 3, 4, 5, 6, and 7 with the extra electron. So this would be completing an octet because there are 8 electrons, and the duplet would be example of hydrogen. So hydrogen will have only 1, and then there will be 1 extra one. So this, it would be completing what? It would be completing a duplet. And just like that, we completed section 3.1. So now we'll move on to section 3.2. Actually, let me leave this page for the ionic. Section 3.2, which is what? Which is metallic bonding. Metallic bonding is, in my opinion, very interesting and perhaps maybe one of the easiest types of bond. So let us, I don't know how to get rid of these, that's fine though. Let us discuss how metal bonding looks, or how does it occur. First of all, we have that metal atoms are closely packed together in a lattice. So metal atoms are closely packed together in a lattice, right? Now, how does this lattice look like? It's in the form of a cation surrounded by a bunch of delocalized anions. So the lattice is in the form of a cation surrounded by delocalized electrons, E minus. Now, why is metallic bonding considered strong? Well, very simply, we know that metallic bonding is strong because of the strong electrostatic forces of attraction between the positive metal nuclei and the negative delocalized electrons. So let me just try that. Metallic bonding is strong because of strong electrostatic forces of attraction between positive metal nuclei and negative delocalized electrons. Now, how exactly would this look like? Let us take an example, right? Let's take an example of which metal of, let us say we took the example of aluminum metal, Al. We know that Al is 3 plus, right? Let's say we have Al3 plus, Al3 plus, and Al3 plus. So everywhere surrounding it, it's supposed to have 1 minus, 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 and minus, and a minus. So as you can see, there's a bunch of delocalized electrons, right? So very simply, due to the delocalized electrons, the very freely moving electrons, there will be a very strong force of attraction. Now, usually we know that for metallic atoms, the greater the charge, the smaller the ion. So the more positive the charge, the smaller the ion. Why exactly is that? Because the greater positive the charge means that we're taking away more electrons. The more electrons we take away, the greater effect the nucleus has on the atomic radius. So it will pull all surrounding atoms closer together, so thus the ion will become smaller. So based on this statement, we can understand that there are certain factors that affect the strength of metallic bonding. So what are the factors affecting strength of metallic bonding? Well, very simply, the first and most obvious would be the charge of the nucleus, so charge of nucleus. Then after this, of course, we have the number of delocalized electrons. And then, of course, after this, we have the radius of cations, because metals are all cations. Okay? And now we go back to what we said about metals. We said that metals have one of the strongest bonds, you know? Right? So they have one of the strongest bonds. So let us say some of the properties of metals due to the strongness of the bonds, due to the strength of the bonds, and due to the delocalized electrons. Let us see what are the general properties of metals. So some general properties of metals. The first general property of metal is that it has a very high relative melting point and boiling point. So high melting point, high boiling point. Now, why exactly do they have a high melting point and a high boiling point? This is due to the strength of bonds, because they have very strong bonds or very strong electrostatic forces. So this is due to strength of electrostatic forces, okay? And because these electrostatic forces will cause strong bonds, and strong bonds need a lot of energy to be broken, okay? So we just discussed why they have high melting points and high boiling points. Now, of course, we do have a singular exception, okay? This exception is mercury. And what do we know about mercury? Mercury is one of the two liquid elements in the whole entire periodic table, because all elements are mainly gaseous or solid, right? The only two liquid are bromine and mercury at room temperature. But even though mercury is a metal, it still is a liquid at room temperature. Now, why is it a liquid at room temperature? We can say that mercury has very weaker bonds than regular metals, and due to this, mercury's electrons do not move around very freely. So we say the only exception is mercury, which is liquid at room temperature, right? And what can we also say about this? We can also say that it moves. However, the delocalized electrons do not move very freely. Okay, so this is about the states of metal. okay? Because usually metals are solid, and this only exception, which is mercury, we say that the delocalized electrons do not move very freely. Now, after this, we move on to conductivity. We know that metals conduct both heat and electricity, so they conduct heat and electricity. Okay, so let us discuss what does the conductivity of electricity mean to us? How can we explain it based on how we know the structure of the metallic bonds? How can we explain electrical conductivity? Very simply, we can say what? We can say that the conductivity of electricity is due to the free moving delocalized electrons. So this is due to free moving delocalized electrons. And this is not only the case in metals. You can see this where? You can see this in aqueous ionic compounds, and in addition to certain molecular compounds. For example, let's take let's say this is not the case in molecular and solid ionic. Okay, so this is not the case in molecular and solid ionic. However, we have an exception, being graphite. Why do we know that graphite conducts electricity? Because it has delocalized electrons as well. I think we took this last year. And as well with aqueous ionic, same exact thing. They have delocalized electrons. So the conductivity of electricity is due to, in general, the delocalization of electrons, or in other terms, free moving electrons. Now we finished discussing electricity. Let's discuss a bit of heat. Heat is not too long. So heat, how is the conductivity of heat caused? It's very simply caused by the vibration between metal ions and its neighbors and movement of delocalized electrons. So heat is transferred, or it's conducted due to vibrations between metal ion and its neighbors, and the movement of what? And the movement of delocalized electrons. And just like that, we finished what? We finished 3.2, which is about metallic bonding. Now we move on to 3.3, which is about covalent bonding. Now 3.3 is a bit long, but it's a nice section. Now we move on to covalent bonding. What exactly is a covalent bond? A covalent bond results from the sharing of electrons between two or more non-metal atoms. So let me write it. A covalent bond results from the sharing of electrons between non-metal atoms. It is an electrostatic force of attraction between the nuclei of the atoms and the shared electrons. So it is an electrostatic force of attraction between the force of attraction, between the nuclei, what did I say? It's an electrostatic force of attraction between the nuclei of the atoms and shared electrons. Perfect. So now, after we finished from discussing covalent bonds, let us see the types of covalent bond. We have a single bond, which looks like this, and it's the sharing of 2 E-, which is one pair. Okay, so 2 electrons, one pair. A double bond, which looks like this, and it's the sharing of 4 electrons, or 2 pairs. And then we have, last but not least, the triple bond, which looks like this, and it's the sharing of 6 electrons, and it is 3 pairs. Okay, Now, of course, there's something we need to mention as well, which is the polar and non-polar bonds. So, polar and non-polar bonds. Now, if atoms are equally shared between atoms of similar electronegativity, they are non-polar. Otherwise, they are polar. So, equally shared between atoms of similar electronegativity are equally shared between atoms of similar electronegativity, then they are what? They are non-polar. Otherwise, it's the opposite, non-polar. Otherwise, it is what? It is polar. Okay? So let's take an example of this. Let's take on the reason why hydrogen H2 is non-polar, whereas HCl is polar. Very simply, if we drew H2, it would be H single bond H, and HCl is H single bond Cl, right? So, H and H have the same electronegativity, right? That means they will equally share the electron. Whereas Cl has a greater electronegativity, so most of the electron will go to Cl. This is the definition of polar and non-polar. How do we know if one element is more polar than the other? Of course, as we go across the period, it's more polar. Down the group, it's what it is less polar. Or you could memorize this, Falkland-Birch. So Falkland-Birch helps us to see which is most electronegative. Here is the most electronegative, and here is the least electronegative. So as you can see, if you're comparing chlorine and hydrogen to hydrogen and hydrogen, definitely chlorine has a higher electronegativity than hydrogen, so it will fully attract the it will fully attract the electron. So actually, if we were to draw how it looks like, this would look something like this, right? Whereas this over here would look something like this, you know? Now, do you remember the very first thing we said about bonds? Let me go back all the way here. What did we say about bonds? We said atoms tend to obtain a full valence shell to become more stable and decrease their energy by forming bonds with other atoms. Now, this is a very main reason why most gases are diatomic, okay? So, if they asked why most gases are diatomic, we say that it is due to their bonding because they want to decrease their total energy and become more stable and obtain a noble gas configuration. Alright, so now we move on to a definition that we're going to see later on. I don't know if it's in this section or the next section, but it is what it is, the bond length. What's the definition of a bond length? Bond length is a measurable distance that exists between the nuclei of two atoms that are bonded covalently. So this is the definition of a bond length. Okay, another thing we will learn is bond energy. What is bond energy? Bond energy is the energy needed to break chemical bonds. Energy needed to break chemical bonds. Now, at the distance of the bond length, okay, we know that the potential energy of the system is the lowest possible that it reaches. Now, because it's the lowest possible that it reaches, we can also find from this same point what? The bond energy. So, this potential energy, even though it's the lowest, it has the same magnitude, but the opposite sign of the bond energy. So, if we have the potential energy, we will be able to find the bond energy. Okay, so there's a graph that may come in the exam, and it will look something like this, if I'm not mistaken. Over here, we will have 0, and this is what? This is the potential energy in kilojoules per mole. And over here is the internuclear distance. So this is the internuclear distance in nanometers. So of course, we start potential energy being at plus infinity, right? but like this is just theoretically speaking. If it starts at plus infinity, it will decrease until it reaches here, right? And then it will come here, and then it will come and end up being like this. I think I should move the 0 a bit lower then. So it should be here. So what exactly can we understand from this graph? First of all, this is the distance between one nucleus and the other nucleus, right? So from this graph, we can say that the smaller the distance, the smaller the possible distance, the greater the potential energy, right? Then it keeps on decreasing until it reaches the lowest possible point over here. This lowest possible point over here, on the x-axis, we can find the bond length, right? This is the bond length. Whereas on the y-axis, we can find what? We can find the bond energy. But remember to put it in what? To put it in absolute value, okay? So after this point, if the distance keeps on increasing, it will, like, the potential energy will go up all the way until 0, and then at infinity, it's what? It is practically 0. So the energy, potential energy at infinity, the farther they are, the less the potential energy. And this, of course, we can derive it from a rule that's similar to Coulomb's rule, but this rule is that the energy is equal to charge 1 times charge 2 times k, of course, over what? Over the distance. Okay, so they're not proportional or inversely proportional to the square. It's inversely proportional only, not to the square. We're talking only about the internuclear distance. Okay, so this is very simply the graph. Okay, now after that we can move on to single, double and triple covalent bonds. We first of all, I don't think it wants me to zoom in. There we go. We first of all start off with the single covalent bond. For example, Cl single bond Cl. Okay, single covalent bonds happen when two atoms share 2 electrons to achieve stability. 2 electrons, that means we have 1 electron from Cl and 1 electron from the other Cl. Now, how do we represent this? We have 2 ways to represent this. Either like this, you draw Cl, and then Cl again, and then you draw what? You draw the dot and cross graph. So you have, oops, what happened? Undo. Okay, so then what do you have? You have here the crosses 1, 2, 3, 4, 5, 6, and 7, exactly. And then here it would be, let's say it's dots, not crosses. Here it would be 1, 2, 3, 4, 5, 6, and 7. So as you can see, the intersection over here is where they are sharing the 2 electrons. So it could be either represented like this with the intersection. Of course, you don't draw them on the line. You should draw them. In fact, it's wrong to draw it like this. Let me see in the eraser. Is there an option for the top eraser? Oh no, there's no. Hold on. Okay, so it's supposed to look, in fact, like this. 1x from the Cl and 1 dot from the Cl. It should be in the intersection. Now, of course, if you want to represent it by the Lewis structure, it would be Cl, single bond Cl, and don't forget to draw the surrounding valence electrons. So it would look something like this. This is very simply most of what I want to say about single bonds. Okay, so this is a single bond example. Let us take a double bond example. Let us say O2, right? Double bond, we will take O2. So O double bond O. How do we represent this? First of all, we start with the intersection. O here and O here. This is a bit confusing, but pay attention. How many valence electrons does oxygen has? Or does oxygen have? Oxygen has 6 valence electrons, right? So it's gonna be 1, 2, 3, 4, 5, and 6. Perfect. Then the other oxygen, same exact thing. It will have 1, 2, 3, 4, 5, and 6 valence electrons. Now, as you can see, these electrons are unpaired, so we don't like to see any electrons that are unpaired, so we're gonna get rid of these. And where will we place them now? We will place these electrons right next to the other ones, right? So now it's supposed to look something like this. And remember, of course, you don't draw them here. Instead, you draw them in the middle. So it will be X, X, and dot, dot. So it should look something like this. Okay, this is if you're drawing the intersection. And of course, if you're drawing the Lewis structure, you're supposed to have the surrounding electrons. So it should look what? It should look something like this. This is for the double bond. And now we move on to what? We move on to the triple bond. So triple bond. How does the triple bond look like? Let's take an example. N triple bonded N. So of course we can draw the intersection. We know that nitrogen has 5 valence electrons. So it will be 1, 2, 3, 4, and 5 here. And then 1, 2, 3, 4, and 5 here. So as you can see, even though these are in the intersection, we also have this over here. And this over here. They are what? They are unpaired. So what do? We'll move them all the way over here. So now it looks something like this. It will look like we have one lone pair on nitrogen, another lone pair on the other nitrogen, and the intersection has 3 electrons. So this is the triple bond. And another way you could represent it is what is the N triple bond N 1, 2, 3, 4. Now, how do I make sure my work is correct? I need to count for each electron. I need to make sure it follows either the duplet or the octet rule. If it follows the octet rule, it needs to have 8 valence electrons. So this has 1, 2, 3, 4, 5, 6, 7, 8. Perfect. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. So Cl, single bond Cl is done. This has 1, 2, 3, 4, 5, 6, 7, 8. Perfect. This is 1, 2, 3, 4, 5, 6, 7, 8. Perfect. So both the O2 is also done. Now, 1, 2, 3, 4, 5, 6, 7, 8. Here is done. Then 1, 2, 3, 4, 5, 6, 7, 8. This is also done as well. So as you can see, as long as each atom completes the octet rule, which is having 8 electrons in the valence shell, then it is good to go. Now that we finished, I'm gonna move on to how do we draw atoms in general. This method is called the Lewis structure. So what are the rules of Lewis structure? We have a couple of rules. I separated them different from the book because I found that they added some extra unnecessary rule. Okay, so let's start with the first rule. The first rule is to count the group number of all atoms. Okay, this is what? This is the number of valence electrons. If the atom is an anion, for example, CO3 2-, you will add the charge. You will plus charge. Okay? If it is a cation, for example, Mg2+, okay? Or no, I can't think of, for example, NH4+, right? You will subtract the charge. Okay? Because we are dealing with the number of electrons. Okay? So you will subtract the charge. This is the first very step. Second step is to choose a central atom. Okay? What are the conditions for a central atom? It must be the least negative, and you can use it by following the Falkenbridge rule. Okay? And what? It's never ever at all hydrogen. Okay, and also another condition is that oxygens never bond to each other unless it's in peroxides and superoxides. So oxygens never bond to each other unless in peroxides and superoxides. Okay, so this is a very important ideal rule to know on whether or not you should select this atom to be the central atom or not. In most cases, for example, if you took CH4, it's the first letter. So in most cases, it's usually the first letter, which is the central atom. Now, after that, we move on to a new page and a new color. Step 3, use single covalent bonds to link remaining to the central atom. So to link remaining atoms to central atom. To link remaining atoms to central. Okay, so the third step is to use single covalent bonds to link remaining atoms to the central atom. And then I believe the fourth step, not the last step, is to distribute remaining electrons as lone pairs on surrounding atoms, then on central only if the central atom is after period 2. Okay, so this is the fourth step. And now the fifth step, what do? We do to check if the octet rule is complete. If octet rule is not complete, then what do you start doing? You start with the double and triple bonding. Okay, so this is all of the rules. Let me try and zoom out as much as I can. I don't think it will let me. But here I'm trying my best. I don't think. It's fine. So this is all of the rules for the Lewis structure. So let's take a practice example on this. So for example, let's say we want to draw, let us say that we want to draw carbon dioxide. This is just an example, right? So the very first thing that we start with based on the rule is to count the group number of all atoms, right? So carbon is in which group? It's in group 4. Plus oxygen is in which group? It's group 6, and we have 2 oxygens, so 6 times 2. And we don't have any charge, so it's just gonna be like this is gonna be equal to what? Is not gonna be equal to 0, my bad. It's gonna be equal to, let me get my calculator. 4 plus 6 times 2, it's gonna be what? It's gonna be then 16. What does 16 mean? That means 16 electrons should be found in total in the CO2. So first thing we do before we proceed is we kind of choose a central atom, which in our scenario would be carbon, because based on Falkland Bridge, the carbon is less electronegative than the oxygen. Okay, so that means surrounding it we have oxygen here and oxygen here, and we said that we use a single covalent bond to attach the two. Perfect. Now, what did we say? We said that we had 16 electrons and we will subtract 4. Why? Because we used 2 electrons here and 2 electrons here. So in total, we have already used from the covalent bonds 4. So 16 minus 4, that's going to be 12 electrons. Divide that by 2. That's going to be 6 lone pairs. What does this mean? This means on the surrounding atoms, we have to count 1, 2, 3, 4, 5, and 6 lone pairs. Now, what do we need to check? We need to check if all the atoms are completing the octet. Let us see. Over here, this is completing the octet. How do I know? I have 1, 2, 3, 4, 5, 6, 7, and 8, because these are considered as 2. The carbon is not completing the octet. And over here, this is also completing the octet. So how do we fix this in order for the carbon to be completing the octet? Well, very simply, you will take an electron from here. You will take the lone pair and you will give it to the carbon. So now it's a double bond. And you will do the exact same thing over here. So now, as you can see, this should be the structure of CO2. This is the Lewis structure of CO2. Okay, perfect. We finished the Lewis structure. Now we need to talk about the formation of certain covalent bonds. Okay, so the formation of covalent bonds. Covalent bonds are formed when 2 nonmetals, okay, combine orbitals to share their, this is an R, to share their electrons. Okay, the combined orbital is called a molecular, what's up with my spelling today? That's nice. Molecular orbital. Perfect. Let's take an example. This example would be what? Would be hydrogen, single bond, hydrogen. do you know the configuration of hydrogen? It's 1s1 and 1s1. So if we were to draw the orbitals, the s orbital is like this, right? If we were to draw the orbitals, it would be plus, plus, right? So hydrogen, hydrogen. The plus is the nucleus, and they will come together. They will make a bond together, and they will form what? A combined orbital, which will look like this. Okay, so this is H. This is the orbital of H single bond H. So this is the definition of a molecular orbital. Now we have two different types of molecular orbital. They are the sigma orbital, which looks like this, and the pi orbital, which looks like this. The only specific difference between sigma and pi is that sigma has only one intersection and pi has two or more, two plus intersection, two or more intersection. And about the sigma is that it is stronger and less reactive than the pi bonds. That means the pi is weaker and more reactive than the sigma bonds. Okay? Perfect. So now, after this, we move on to a new concept, which is hybridization. Hybridization is the mixing of atomic orbitals. So what do I mean by mixing? For example, let's say I have 1s and 3p orbitals, because you know it's 1s, and then we have, because when you draw the s orbital it's one box, and the 3 orbital it's 3 boxes, right? So let's say I have 1s and 3p orbitals. It will turn out as an sp3 orbital, which looks something like this, right? So this is the sp3 orbital. Of course, they're all connected, okay? Now, let's say I had 1s and then 2p orbitals. It would look like this, and this is what? An sp2 orbital. Now let's say I had 1s and 1p orbital. It would look like this, and this is what? This is an sp orbital. Now, what do we need to know? Very simply, we're talking about bonds. A single bond that looks like this. It is very simply one sigma bond. A double bond, on the other hand, which looks like this. I forgot to mention that this is sp3 hybridized. Okay, a double bond, which looks like this, has a sigma and a pi bond. So it's one sigma and one pi bond. And it is what? It's an sp2 hybridized. Then finally, a triple bond, which looks like this, is sigma, pi, pi, right? So it's one sigma, two pi, and it's what? It's an sp hybridized. So just like that, we finished the third type of bonding, which is covalent bonding. Now we move on to the fourth type of bonding, which is coordinate or dative bonding. Now, what about this type of bonding? Technically, it is a covalent bond, but it is when both electrons come from only one of the atoms. So, coordinate bonding, dative bonding, is when two atoms form a covalent bond, but both electrons come from only one of the atoms. Now that I'm saying this, it may seem a bit weird to imagine, but let's take an example. Let's take when NH3 is added to H plus, we will get what? We will get an H4 plus. So how will an H4 plus look like? First of all, let us draw an H3. So let's follow the Lewis structure of an H3. N is in group 5, if I'm not mistaken, plus hydrogen being in group 1, so plus 1 times 3. So that's gonna be in total 8 electrons, right? So it's gonna be NH3. Now we give each one of them a bond. Perfect. So how many covalent bonds do we have? We have 3 covalent bonds, meaning we used 6 electrons. So 8 minus 6 is 2. That means there should be 2 electrons left, right? But now one of very important things is that hydrogen does not get what? Hydrogen does not get electrons. So I forgot to mention, I believe in the Lewis structure, is that hydrogen does not get any electrons. So if we were supposed to give our electrons, we will give it to the central atom. And it will look something like this. Okay, now what happens next is that we will add the hydrogen H+, right? I think the color is a bit too strong. Let me change it. Hydrogen H+. Now, what are the conditions in order for us to have what? In order for us to have a coordinate bonds, we should have one lone pair and one deficient atom. So one lone pair and one deficient atom. As you can see, we have a lone pair, and over here it's a deficient atom. It's deficient of electrons. So together they will come and they will form what? And they will form the NH4+, right? So it will look like what? It will look like this. So if you want to represent it better, because it's plus, you put the brackets, right? And we will put plus on top. Now this is a perfect example of a coordinate bond, and now we will represent what? We will represent a LCl6. Okay, and with these we are learning as well new rules. So I'll need to go back and add that hydrogen does not get, where's the Lewis structure? Was it here? Triple bond, here we go. Yeah, we said that the central atom is never hydrogen, and actually, I will make a new page and I will add these extra rules, is that hydrogen can never get extra electrons, and we have some electrons that are, elements that are allowed to be electron deficient. For example, we will see one in the next scenario that we're going to be drawing, which is Al2Cl6. It looks a bit complicated, so let's separate it into AlCl3 and AlCl3, right? We will draw 2 times AlCl3. So we have AlCl3, right? And then we also have AlCl3. Now you may be wondering why I drew it this way. Well, very simply, it is for the dative bond, for the coordinate bond, in order for it to function. Now, let us see. I'm gonna leave you guys to do the Lewis structure, but it's supposed to look something like this, right? And you will notice that our central atom is gonna be what? It's gonna be electron deficient. But it's okay for these 3: boron, beryllium. Was it boron or barium? I think. No, sorry, it's not barium. It's boron, beryllium, and aluminum. These 3 are allowed to be electron deficient. It's okay for them to be electron deficient. Big check. Okay, it's totally fine for them to be electron deficient. Okay. So, due to this, aluminum, it's fine for it to be what? It's fine for it to not have an octet. So now, we complete the rest, and we said aluminum, it's fine for it to not have an octet. So now, since it does not have an octet, look what happens. This is electron deficient, this is a lone pair, so they will link to each other. And this is electron deficient, and this is what? This is a lone pair. They will link to each other. So we represent coordinate bonds by an arrow whose head points away from the lone pair towards the deficient atom. So it's supposed to look what? It's supposed to look something like this, okay? So what did we learn new from this? Is that hydrogen can never get any extra electrons, and boron, beryllium, and aluminum can be electron deficient, okay? So now we move on to what? We move on to some simple definitions and a conclusion we take from these definitions. Bond length. We described this before, but now in a simpler term, bond length is the distance of the nuclei, or between the nuclei of 2 covalently bonded atoms. So bond length is the distance between the nuclei of 2 covalently bonded atoms. Perfect. What's the next thing we're going to define? We're going to define bond energy. We also defined bond energy previously, but now we're going to change it into something more general. It is what? It is the energy needed to break 1 mole of a particular covalent bond. Okay? And now, the new thing that we're gonna be defining is what is the bond order. Bond order is basically how many bonds we have. Or in some other sense, it's the bond strength or number. So bond order is the bond strength or number. Now, what can we deduce from this? Very simply, we can say the greater the bond order, the shorter the distance, the smaller, the shorter the distance, or we say the bond length, which is better to say, the greater the bond energy, the greater the energy needed to break this bond. Perfect. So, perfect, just like that, we finished what we finished 3.3. Now we'll move on to the next chapter, which is 3.4, and it talks about resonating structures. So what are resonance structures or resonating structures? So resonance structures. They are when molecules have more than one valid structure. So resonance structures occur when molecules have more than one valid structure. For example, we should take CO3 2 minus as our example, and let us draw the 3 possible ways. First of all, we start with CO3, right? And we say that carbon is in group 4, oxygen is in group 6, and we have 3 oxygen. Now, it is what? 2 minus, so we need to add 2 electrons. So in total, that's going to be 24 electrons. Now we subtract from it 6 because we used 3 already covalent bonds that are single. So 24 minus 6, this will give us 18. Divide this by 2, this will give us how much? 9 lone pairs. So we need to work with 9 lone pairs. I'll move it here. So we need to work with 9 lone pairs. We can do 1, 2, 3, 4, 5, 6, 7, 8, and 9. Perfect. But now here's the scenario. All of them complete the octet except for carbon. So we can take, for example, this lone pair and we can turn it into a double bond. So now it looks like this. This is the first way that it can be drawn. Now, don't forget here to include the minus because this is the formal charge of the atoms. We're going to discuss formal charge later on. This is the first way to do it. The second way to do it would be to have it all the same, right? Everything would be exactly the same, except that here you would have the double bond. So you will change the place of the double bond. This is the second place to do it. Now, the third and last place, like the third and last way to do it would be like this, right? So what we understand from here is that as long as the double or triple bond can change and move, this is a resonating structure, okay? So, in the resonating structure, how do we calculate bond orders? Bond orders on the bond in a resonating structure is always fractional. So how do we calculate it? You will choose one specific atom. For example, I choose this oxygen over here. So I will always move with this oxygen over here. So it will be, what is the bond order here? We have 1 bond. Here we have, so here's 1 bond, here's 2 bond, here is 1 bond. So it's 1 plus 2 plus 1 divided by the total number of structures, which is 3, and you will put it on the calculator and you will get 1.333. So that is it pretty much for resonance structures. Okay, so now after this we can calculate what? We can calculate the formal charge. What about the formal charge? The formal charge is the charge an atom would have had if its bonding electrons were equally shared between the bonded atoms. Would have had if its bonding electrons were equally shared between bonded atoms, okay? And it is used, why do we use the formal charges? We use the formal charges in order for us to choose the most appropriate structure. So to choose the most appropriate structure. Okay, how do we calculate the formal charge? It's very simple, very easy. It's very simply the group number minus the number of surrounding electrons, and this is how you calculate the formal charge. Now, what are some conditions that we need to know of stability? Let me just write here conditions of stability. Okay, first of all, it should have a central atom having a formal charge of 0. This is more preferable, formal charge of 0. And it should have most atoms having a formal charge of 0. Okay, so this is pretty much it for this video. 3.5 and 3.6 are all equations. 3.5 is about molecular mass, empirical formulas, and 3.6 is about water of crystallization. Very simply, it's water that is found in crystals when formed. So there's actually not too much to write here. But anyways, that's it for this video. Thank you guys for watching. I hope you enjoyed and have a wonderful day. Let me just reach the top. And we reached it over here. Thank you guys for watching. I hope you enjoyed and have a wonderful day.